Hey everybody, welcome to Lecture 7, Mathematical Induction, that's in your Analysis of Algorithms course. So what we're going to do today is we're going to go through some idea of what mathematical induction is, and we're going to use it to prove a result on a graph. Now the thing is, I know you guys have actually done mathematical induction in math, so I'm not going to be too tight on things like definitions and stuff. You guys have seen all of that. What I am going to do is give you a bit of an analogy of how induction works. Okay, so here's an example. Here's something that I think is illustrative of how induction works. So let's say my goal is to steal Steve's title of meme lord. You guys had Steve lecturing last year. You know he's the lord of the memes. But now I'm going to dethrone him. So for me to dethrone him, I need to make sure everyone gets hold of my memes. So let's say there's an infinitely long line of people. I want one of my memes to go to every person in this line, right? So if I reformulate that in a bit of a more mathematical way, I could say that if I make the statement person n has my meme, I want that statement to be true for every natural number n, right? That'll mean that everybody has my meme. So you might say the most obvious strategy is just send my meme to everybody. But there's an infinite number of people to send it to. And you guys know me well enough to know that I'm way too lazy to do an infinite amount of work. Okay. So what I want to do instead is I just want to send it to the first person. Now, me having sent it to the first person means that if I look at the statement person n has my meme, that's true for n equals 0, right? Because person 0 has my meme. Okay. But that meme of me with my lightsaber is not particularly good. So that's all that happens. Person 0 has it, and they're not going to pass on my meme, and it just gets stuck. The statement won't be true even for n equals 1. Person 1 will not have my meme, and person 2 won't have it. Basically, the only person who has it is person 0. But what if I make a meme that's so good that if someone has it, they're compelled to pass it on. They can't just hold on to it because it's too good. Haha, now that's a better meme. Okay, so if I'm using that meme and I send it to person 0, person 0 has to pass it to person 1 because it's just too good to hold on to. Okay? Similarly, person 1 has no choice but to send it to person 2. And person 2 has to send it to 3 and 4 and 5 and 6 and so on. Okay? More generally, I could say that person k is compelled to send it to person k plus 1 for all k. Okay? So if I wanted to get to the point where the statement person n has my meme is true for all n, I needed to do two things. The first thing was I had to send the meme to somebody. So I had to ensure that my statement person n has my meme was true for n equals 0. Okay? So I had to send my meme to person 0. That in induction is called the base case. Okay? That would have gotten me sort of halfway there. The next thing I need to do is ensure that my meme would definitely be passed. So what I'd want to say is that if person k has my meme, then person k plus 1 automatically has it, right? Again, in math, I could say if the statement person k has my meme is true, then person k plus 1 has my meme is also true. Okay? This is called the induction step in mathematics. Okay? Now, the reason that this makes the statement true for all values is that, as you can see, the post sort of goes viral, right? If person 0 has it, person 1 has it, and person 2 has it, and it just keeps going on and on and on until person infinity has it. Okay, so fundamentally it becomes true for all people in this infinite list. Okay, so is this useful with graphs? Can I use the same logic to prove results about graphs? Okay, so let's pick some fairly difficult thing to prove. Let's look at this statement. If I say there's a graph G, right? Graph G is made up of vertices and edges. And the vertex that has the biggest degree is vertex V, right? It's the vertex that has the most edges. And it has degree R. So the number of edges that it has is R. My statement is that that graph will always be R plus 1 colorable, meaning I can perform graph coloring on it using R plus 1 or less colors. Okay, that last definition is quite important. When I say something is R plus 1 colorable, that doesn't mean that the minimum number of colors I need to color it is r plus 1. It just means that if I had r plus 1 colors, I could perform a valid coloring of that graph. Okay? Now, this is quite an unpleasant statement. I mean, it's quite a big one, because basically I'm making a statement about an entire graph, right? I'm saying the graph G is r plus 1 colorable. But I'm saying it on the basis of one vertex. I'm saying that this one vertex V, which has maximum degree, has degree R. So, if you think about it, there's an infinite number of possible graphs, right? If I told you to draw an arbitrary graph, I mean, you could pick anything. There's just any number of possible graphs. Now, the only thing I know about this graph, the only thing that restricts it, is the vertex with the biggest degree. So let's say I had a graph, and the vertex of biggest degree has degree, say, 7. So I'm looking at this example. You can see there's a vertex V which has 7 vertices. And I've intentionally faded out on the end of these edges, because what I'm indicating here is that I know very little about the rest of this graph. The rest of this graph could have any number of vertices and edges, and I know nothing about them except that the rest of the graph doesn't have a vertex with a degree greater than 7, right? Because this V was the vertex with the maximum degree. Now I'm saying that the entire graph can be colored using 8 colors, right? R plus 1 colors, where in this case R is 7. And that's true no matter what the rest of the graph looks like. And that's kind of insane. And because it's kind of insane, it's kind of insanely hard to prove. So how do we use induction with this? So remember in our example, we said that we were trying to prove the statement person n has the meme is true for every natural number n, right? So my statement had something to do with n, meaning some number that I can allow to increase and eventually become infinite. If I look at the initial statement, a graph G whose vertex of maximum degree V has degree R will always be R plus 1 colorable, there isn't an n, right? Because the vertex of maximum degree V has degree R. That's the degree of the vertex. I can't change the degree of the vertex. It's R, it just is. So when I want to pick an n that can potentially increase and make my problem size more and more complex, I'll often use n to represent the number of vertices in the graph, right? This is true generally when I'm doing induction on graphs, but it's not always true. It's just commonly true. Then I could rewrite the top statement to be all graphs with n vertices whose vertex of maximum degree V has degree R will always be R plus 1 colorable. Yeah, you thought that example was fun, but now I'm hurting you, hey? So pause and think about what that statement means for a while. And once you've got it, just hit play again. Okay, so if I say all graphs with n vertices whose vertex of maximum degree V has degree R will always be R plus 1 colorable, that is only equivalent to the statement on top if I say that this is true for all n. Okay, so I must prove the statement all graphs with n vertices whose vertex of maximum degree V has degree R will always be R plus 1 colorable is true for every natural number n. Okay, so that's a bit of a mind bender, but pause and think about it. Now, I want to prove that the statement is true for every natural number n. Okay? But as I said earlier, that means there's an infinite number of n's, right? And you guys know me well enough to know that I'm way too lazy to prove something true for every natural number n. So what I'm going to do is make sure that it's true for the first n. Now, the first n is where n is 0. So all graphs with 0 vertices. What's a graph with 0 vertices? I mean, that's a pretty easy example, right? There's only one graph with 0 vertices. There's no vertices in it. In there, what's the vertex of maximum degree? It doesn't exist. So the maximum degree is 0, right? If there's no vertices, the vertex of maximum degree doesn't exist, and so the maximum degree is 0. So the vertex of maximum degree has degree 0, so R is 0. So we need to show that this graph is colorable using one or fewer colors. Can we color it using one or fewer colors? I mean, it doesn't have any vertices, so yeah, we can color it using 0 colors because we don't have to color any vertices. So the statement is true for n equals 0, quite trivially, just because there's no vertices. The thing about that is whenever I do this example in class, people are always a bit up in arms. They're like, that's kind of unconvincing. A graph with 0 vertices tells us nothing. Now, in principle, no, that's wrong. I can use a graph with 0 vertices to be my base case here. But let's confirm with n equals 1. Let's pretend we decided to choose a base case of n equals 1. Okay? Then I'd be saying that all graphs with n vertices whose vertex of maximum degree v has degree r will always be r plus 1 colorable is a true statement for n equals 1. Okay? So meaning all graphs with one vertex. Again, in this case, all graphs is a nice thing because there's only one graph of size 1, right? It looks like this. It's just the vertex 0. Okay? So because there's no edges, because where would the edges go to? They can't go to other vertices because there's no other vertices. There's only one vertex. The size of the graph has one vertex, right? So this is the graph. So what's the vertex of maximum degree in this case? It's this vertex 0, right? And what is its degree? Remember, the degree is the number of edges. How many edges does vertex 0 have? It doesn't have any edges, so its degree is 0. Okay, so if the degree is 0, r is 0. So we're saying this graph is r plus 1 colorable, meaning it can be colored using one color. Can I color it using one color without breaking any constraints? I mean, yeah, I can. There's only one vertex, so I can assign it to that one color, and I'm done. So the statement all graphs with one vertex, whose vertex of maximum degree v has degree r will always be r plus 1 colorable, is true, which is great. So that means I can use my base case. I mean, I know I've got my base case. Either it's n equals 0 or n equals 1 if you were unconvinced by n equals 0, although it was actually perfectly fine. Then, my base case is done. Now, remember, if my meme wasn't good enough, it doesn't get passed on and it just gets stuck at the base case. So I need to show now that this sort of truth gets passed on, right? In the same way that the meme does. So that means I can say that if the statement all graphs with k vertices whose vertex of maximum degree has degree r will always be r plus 1 colorable is true, then all graphs with k plus 1 vertices whose vertex of maximum degree v has degree r will always be r plus 1 colorable is true. Okay? So all I've changed is that k to a k plus 1. Okay, so this was similar to, like in the base case, it was similar to showing that the first guy has the meme. Right? Now this other part of proving that if it's true for k, it's true for k plus 1 is similar to saying that anyone who has the meme is compelled to pass it on. Right? Because then it'll eventually mean that all infinite people will have it. Okay, so when we're doing this step, which is called the induction step, we're allowed to assume the first part. We're allowed to assume this part. Okay, so we can assume all graphs with k vertices whose vertex of maximum degree v has degree r will always be r plus 1 colorable is true. Okay, and we call that our induction hypothesis. And we must use that induction hypothesis to prove that all graphs with k plus 1 vertices whose vertex of maximum degree v has degree r will always be r plus 1 colorable is true. Okay, so let's look at how we do that. The trick is, what we'll do is we'll pick an arbitrary graph G that has k plus 1 vertices, whose vertex of maximum degree V has degree R. Now, do we know that this graph is R plus 1 colorable? No, we don't, because we're talking about a graph G with k plus 1 vertices. So we know nothing about this thing, okay? Now, this is a bit problematic because, I mean, for me to apply any logic to this situation, I have to know something. In this case, I know nothing, except that this thing has k plus 1 vertices. So what I'm going to do is, I know that the vertex of maximum degree is vertex V. So I'm going to remove it from graph G to produce graph G prime. Okay? And I'm going to have to take all the edges with it, because the edges have to go to some vertex. If I took out the vertex, I have to take out its edges, right? So I've now got a graph G prime. Now, if G had k plus 1 vertices and I removed one vertex, then G prime is going to have k vertices, right? I hope that makes sense. It just has one less vertex than graph G. Now in G prime, there is a vertex that has a maximum degree. Let's call it U. Now this vertex U, since we haven't added any edges, it must have a degree that's less than or equal to R, right? Because if its degree was greater than R, then its degree would have been greater than R in G as well, right? But G had a maximum degree of R, okay? So U has a degree that's less than or equal to R. But G prime has K vertices and a vertex of maximum degree U that has a degree less than or equal to R. So G prime must be R plus 1 colorable by our induction hypothesis. So basically by this assumption, because G prime is a graph with K vertices, I'm allowed to use this assumption, right? And so that means that G prime must be R plus 1 colorable because this statement must now hold, right? Again, remember the key to this is that R plus 1 colorable doesn't mean that I need to use all R plus 1 colors, right? It might be possible to color it using R colors or R minus 1 colors. It doesn't matter. As long as it's colorable using R plus 1 colors, we're fine. Okay, so G prime is R plus 1 colorable. But I don't care about that. I was trying to prove that G is R plus 1 colorable. Okay, so now we know G prime is R plus 1 colorable. What we can do is we can reconstruct G by taking G prime and adding V and its edges back. Okay, so remember we produced G prime by just taking V and its edges out. So now we're going to produce G again by adding V and its edges back. Okay, but we're going to keep the colors we had from G prime, right? So now in G prime, we know that coloring was valid with our R plus 1 colors, right? So we're going to keep that color, those colors. So then the only vertex that won't have a color is vertex V, because it's the only vertex that we added into G prime. Okay, so now we have to see what we can do about V's color. Now we know V has degree R, right? Meaning it has R neighbors. Now remember with graph coloring, we can't use the same color that a neighbor used. Okay, now V has R neighbors, so at most R colors can be used up by its neighbors. So that means if we had R plus 1 colors, there's one left over for V, right? V can use the R plus 1th color. So that means G is R plus 1 colorable just by keeping the same R plus 1 coloring from G prime and adding V back and using that one leftover color. Okay, so what we've proven here is that an arbitrary graph G with K plus 1 vertices, whose vertex of maximum degree V has degree R, is R plus 1 colorable. Okay, and we sort of did it by induction. Now, the really cool thing about this, what makes induction such a powerful thing, is this base case. We always choose it to be really easy to prove, right? So we chose a graph of size 1, and then it really didn't hurt us to try and prove that all graphs of size 1 were satisfied the condition above, right? So we deliberately picked it to be easy. Then, instead of trying to prove this result for an infinite number of graphs and, you know, up to graphs of infinite size, which would have been impossible, we said, let's just prove that if it's true for size K, then it's true for size K plus 1. And that kind of spread like a meme and meant that every graph was eventually sent the meme or given the truth property, if I can put it that way. Okay, so I hope that made a bit of sense. If not, let me know on the WhatsApp group and I'll do my best to clarify. Thank you, everybody.